So we're going to use those same 4 strategies to estimate an area of a figure we already know. So we have a semicircle with a radius of 4. And our goal is to find the shaded area of the semicircle. Well, it's a semicircle, so we already know how to find the exact area, right? Right. It's half a circle. So that would be half of pi r squared. So the area would be half of pi r squared. Well, that's 16. Half of that would be 8 pi. Let's find out that exact area. Now the exact area is a decimal. Using our calculator is 25.133. That's what we're trying to get to. We're going to see if these estimations can get us close. So we're going to start with the left-hand sum, and we're going to make 4 rectangles. So that means I'm going to divide up my rectangles here, 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 and here. So those are my bases. And if I'm doing a left-hand sum, that means I start with the left side, and I'm using that height as the height of my rectangle, which means, there we go. Okay, so the next rectangle would be that tall, left-hand side. This next rectangle would go all the way up to there. And this last rectangle would have a height on the left side to there. And so we need to find the area of each of those 4 rectangles. Well, the area of the first one is 2 wide and 0 tall. And the next one is 2 wide and square root of 12 tall. 2 wide and 4 tall. 2 wide and square root of 12 tall. And we can put that into the calculator and find out that estimation with a left-hand sum. And it comes out to be 21.856. That's not really that close. Well, what if we divide it up into 8 rectangles? Okay, so now instead of having a width of 2, it's going to have a width of 1. So here's our really skinny one. This one's going to go here. Then this tall. Then that tall. So remember, we're looking at the left side to find out our height. Left-hand sum. Notice that on the left side of our semicircle, all of our rectangles are under the curve, and on the right side, they're over the curve. So here we have 1 wide and 0 tall, 1 wide and square root of 7 tall, 1 wide and square root of 12 tall, 1 wide, square root of 15 tall, 1 wide and the square root, and 4 tall, sorry, 1 wide and another square root of 15, 1 wide and a square root of 12, and then 1 wide and a square root of 7. Excuse Meg in the background. So I'm going to put that in my calculator and find out the estimation with 8 rectangles. So when I add all that up, I get 23.966. That's a little bit closer. What do you think would happen if instead of 8 rectangles, I went to 16? Or 32? Would we be closer? We're still getting an underestimate, right? But we get closer with more rectangles. Now let's do the same thing, but using the right-hand sum. So we're going to start with 4 rectangles. We're going to divide it up into here, 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 and here. But this time we're going to use the right hand or right side of each of those rectangles for our height. So the right side would go up to here, go across. That'd be the height of my rectangle. This one would have a height all the way up to 4. This one would have a height to here. And this one would have a height of 0. So 2 times the square root of 12 plus 2 times 4 plus 2 times the square root of 12 plus 2 times 0. And if I add all that up in my calculator, I get 21.856. Why did this end up being the same as the left-hand sum with 4 rectangles? This time I'm over on the left side and under on the right side, but because this is a symmetrical figure, it comes out to be the same. Let's see what happens with 8 rectangles. So 1, 2, 3, 4, 5, 6, 7, and 8. Right-hand sum. So we're using the right side of that rectangle to figure out our height. Right side gives us our height. Right side gives me my height. Right side gives me my height. Right side gives me my height. So I have 1 times the square root of 7 plus 1 times the square root of 12 plus 1 times the square root of 15 plus 1 times 4 plus 1 times the square root of 15 plus 1 times the square root of 12 plus 1 times the square root of 7 plus 1 times 0. That looks familiar. Again, because it's symmetrical, the right hand and the left hand sums end up being the same thing. What about midpoint sum? Is that going to be closer? Now, for midpoint sum, when we're given a figure, we're going to go with the midpoint of our base. So 2 rectangles. That means I'm going to go from here to here, and from here to here is going to be the base of my rectangle. We're going to use the midpoint to figure out the height. That'd be right here. Well, on the other side, the midpoint is going to decide the height. It's going to go right there. So this one is 4 wide and square root of 12 tall, plus 4 wide and the square root of 12 tall. That's going to be 8 times the square root of 12. Ooh, that's a little bit of an overestimate. Notice that the parts of the rectangle that are outside of our semicircle are bigger than these parts that were left out. What would happen if I divided into 4 rectangles, though? 2, 3, 4. Again, we're going to use the midpoint of that base to decide the height. So I'm coming up from the midpoint. That's going to be the height of this first rectangle. Square root of 7. Okay, so the midpoint is going to determine the height. Here, midpoint is going to determine the height. Midpoint determines the height. So here, we're 2 wide and square root of 7 tall. So 2 times the square root of 7. The next rectangle is 2 wide and square root of 15 tall. So is this one. And this one is 2 times the square root of 7. And our estimation is 26.075. That's closer. Remember, our actual area was 25.133. We're still overestimating, but I feel like that's a little bit closer than those right-hand sums. But could I have gotten more accurate on doing 8 rectangles? Would it be closer? Maybe. Now let's try the trapezoidal. Trapezoidal means that we're going to make trapezoids underneath the curve. So we're going to divide it into 4 trapezoids. 1, 2, 3, 4. I'm going to make a trapezoid out of each of those. So the first one, well, that's as high as that one goes, up to there and there. That's actually a triangle. This one truly is a trapezoid. Base 1, base 2, this would be the height of the trapezoid. Kind of have to look at them sideways to see them as a trapezoid. And then that would be the last one. Okay, so a trapezoid is 1/2 base 1 plus base 2 times the height of that trapezoid. So if you think about them sideways, that's the trapezoid, base 1, base 2, and that's the height. I like to think about it as the average of my bases times the height. So the height is 2, and we're going to take base 1 plus base 2 divided by 2. This one is 2 wide, or 2 tall. Base 1 is square root of 12. This base is 4 tall, divided by 2. Plus 2, base 1 is 4, plus base 2 is square root of 12, plus the last one. Base, height is square root of 12, and the next one is 0, divided by 2. And when I put that in my calculator, plus I get 21.856. How does that compare to the left-hand and the right-hand sums when we used 4 rectangles? Well, if I look back, left-hand sum was 21.856 and right-hand sum was 21.856. Interesting. Notice it is definitely an underestimate for each side, but it comes out the same as if we did left-hand sum or right-hand sum. If I go with 8 trapezoids, excuse my table for creaking, this is an old dining room table. make a trapezoid out of each one. Ooh, this is getting closer, isn't it? Really, really close to the edges of this curve. Looks a lot closer than some of our other figures, huh? Okay, so the width is 1, so I don't really need to write that down. And then I've got 0 high and square root of 7 high, so 0 plus the square root of 7 divided by 2 plus square root of 7 plus square root of 12 divided by 2, square root of 12 and square root of 15. And then square root of 15 plus 4 divided by 2. And notice that it's the same exact trapezoids on the other side. So I'm going to get my answer there and just multiply by 2 because they're exactly the same. Let's see. Square root of 7 divided by 2 plus square root of 7 plus square root of 12. And if you want to see how I'm putting them in the calculator, I'm actually putting them in as fractions so that I don't make mistakes. Whoops, I forgot to do a fraction there, so hold on, let's delete that. Fraction, alpha and your y equals, get you a fraction. We want square root of 12 plus square root of 15 over 2. And then the last fraction was square root of 15 plus 4. Square root of 15 plus 4 divided by 2. Now that gives me the left side, and the other side's exactly the same. So 23.966. Let's see how that compares to the left and right hand estimates. Left hand sum with 8. 23.966. Right hand sum with 8. They come out to be exactly the same. Now, if we increase the number of rectangles, we'd get closer and closer and closer. So how could we find the exact area? We would have to have an infinite number of rectangles. I mean, like itty-bitty little rectangles. And we're going to say that they get so small that that width is really, really, really tiny, infinitely small. We call it dx. I mean, like, it's a sliver, and we'd have to have a whole bunch of them to add up to give me my exact area. So let's think about what the area of each one would be. We'd have dx, a really, really small width, and the height would always be, well, it'd be almost exactly the height at that one single point, right? So for each of those rectangles, if I zoomed in on them, I'd have a rectangle with dx width and f of x tall. That would be ideal, right? So each area would be f of x tall times dx for the width. If we combined them all together, we'd have f of your first x value plus f of your next x value plus f of the next x value, infinitely going. So plus dot, 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 dot. Or we might say that we have a summation of all the x's from A to B, from the first x value to the ending x value of f of x dx. Now in calculus, instead of actually using the summation symbol, we use this symbol, which is called an integral. It's doing the same thing. It's taking all those f of x's times dx and adding them up for us. Now, I'm going to show you how you can use the calculator to find this. So, it'd be the integral. Now, in ours, it went from -4 to 4. Our function, remember it was y equals the square root of 16 minus x squared. So, the square root of 16 minus x squared dx. So in your calculator, to get that integral symbol, we're going to press, I'm going to show you where I'm pressing, alpha, window. This gives us a whole bunch of good stuff. We have absolute value. We do have a summation there. We have how to take the derivative with the calculator. This is the integral, and then 5 is log base. We're going to use the integral. And notice it sets it up just like we wrote it. We're going from -4 to 4. And the order there is really important. We're going to get to that later. Second, square root 16 minus x squared. And notice it has a place for us to put dx. And that is very important that you put the x there. It tells me, and it takes it a little while because it's adding up all those rectangles. It's 25.133. Let's look back at that original when we actually used the formula for area, 25.133. So if we did make infinite number of rectangles, we would get there. Now, how did this work? When f was increasing, what happened with our left-hand sum? So let's look. When we were increasing, the left-hand sum was an underestimate. When f was decreasing on this side, the left sum was an overestimate. What about concavity? What do you think? If we were concave up and we use the left side to make all of our rectangles, we'd definitely be an overestimate. Concave down, kind of like what we had before, using that left side gives us an underestimate. What about the right sum? Well, when we were increasing, the right-hand sum gave us an overestimate. And when we were decreasing, it was an underestimate. What would happen if we were concave up and we're using the right side? Oh, we'd be under the whole time. If we're using the right side and it's concave down, we're going to be over the whole time. What about with those trapezoids? Well, when I made trapezoids and it was increasing, most of the time that's going to be an underestimate. Decreasing, it's going to be an underestimate. Concave up. Well, let's see. If I drew a trapezoid in here, I'm going to be overestimating. But if it's concave down, it's going to be an underestimate.